So let's do certain problems. This is from the exercise. I'm purposely writing the question numbers. So using mathematical induction, prove the following statements for all n belongs to n. Okay. So we have, question number 2. 2 into 3 plus 3 into 4 plus 4 into 5, so on, up to n terms is equal to n into n square plus 6n plus 11 upon 3. So this is our statement Pn. We will have to write the nth term. Now, can you tell what is the nth term?
N into n plus 1.
No, look carefully. Look carefully. The first
n
term,
plus 1 into n plus 2.
correct. It is n plus 1 into n plus 2. This will be the last term because the first term starts with 2 and 3, not with 1 and 2. So this is equal to n into n square plus 6n plus 11 upon 3. So now let us prove this. What is the first step that we need to do? What is the first step? Any of you?
P1 value.
Yes, P of 1 is true. That means for the first term, this is true. Okay. Check for P1 to be true. Now, P1 is 2 into 3 as the LHS 6. All right, RHS is n into n square plus 6n plus 11 upon 3. Put n equal to 1. So 1 times 1 square plus 6 into 1 plus 11 by 3. So this is 1 plus 6, 7 plus 11, 18 upon 3, which is 6. Therefore, P1 is true. That means for n equal to 1, the statement is true. Now assume that P of k is true. So this means P of k is 2 into 3 plus 3 into 4 plus 4 into 5 plus n plus 1 into n plus 2. Okay, is equal to k plus 1 into k plus 2. So this will be equal to k times k square plus 6k plus 11 by 3. Okay, k square plus 6k plus 11 by 3. Okay, assume that the kth statement is true. Next is, given pk is true, check for whether pk plus 1 is true. P of k plus 1 is true. So P of k plus 1 is 2 into 3 plus 3 into 4 plus 4 into 5, so on. The kth term will be k plus 1 into k plus 2. Now k plus first term will be k plus 2 times k plus 3. This should be equal to k right hand side k plus 1 times k plus 1 whole square plus 6 of k plus 1 plus 11 upon 3. So this will simplify to RHS k plus 1 times, you see k square comes from here, 2k and 6k from here becomes 8k. Then 1 plus 1 from this expansion, k square plus 2k plus 1. 1 we'll get from here, 6 we'll get from here, and 11 from here. 18 upon 3. Okay. All right. This is k plus 1. We have to prove that k plus 1 is this. So take LHS. 2 into 3 plus 3 into 4 plus 4 into 5 plus k plus 1 into k plus 2 plus k plus 2 times k plus 3. This, now this value, this is because P of k is true, this will be equal to this value, k into k square plus 6k plus 11 upon 3 plus k plus 2 times k plus 3. So now we have to simplify this. So this is k times k square plus 6k plus 11 plus 3 into k plus 2 to k plus 3. This cannot be factorized further. So we just need to expand. K cube plus 6k square plus 11k, k cube plus 6k square plus 11k is plus 3 times k square. So 3k square, or I'll do 3 times k square plus 3k plus 2k, 5k plus 2 into 3, 6 upon 3. So we get k cube plus 6 plus 3, 9k square. Now 11k plus 15k, 26k plus 6 upon 3. Oh, this is 18. I'm sorry. Okay. Now we know that k plus 1 is the expected factor. So if k plus 1 is the expected factor, how do you factorize this? Do you know to factorize this? How to know? Okay, this is a side note. How to know whether k plus 1 is a factor? If you remember the factors theorem, for a polynomial, okay, if if p of a, if for a polynomial p of n, p of x, this is the nth degree polynomial. If for a polynomial p of n, p of a is equal to 0, then x minus a is a factor of p of n. Did you know this factors theorem? Any of you? Do you know this factors theorem from class 9th, 10th?
Yes.
No.
Yes.
Do you remember?
No, sir.
Okay. Chaitra, how about you? So if k plus 1 is a factor, then x minus a is a factor, right? So k minus of minus 1. So minus 1 should satisfy this equation. You see here, if you substitute k equal to minus 1, you get this as minus 1. This is positive. I'll just write here for rough, minus 1 plus 9 minus 26 plus 18. 18 plus 9 is 27. Minus 1 minus 26 is minus 27. So this becomes 0. It satisfies that polynomial. Understand? So minus 1, if it's satisfying, that means k plus 1 will be a factor. So this is k plus 1 is a factor. Now k plus 1 is a factor. Now we have to write, because how to find the factor? So go by division. If you remember the division, there are other faster methods to do, but right now, if you remember the division with k plus 1, how do you divide? So k multiplied by k square gives k cube. So k square into k will give k cube. K square plus 1 is k square into 1 is k square. Now what do? We subtract. So this becomes 0. You get 8k square plus 26k comes down plus 18. The next to get 8k square, you have to multiply. You have to get 8k square. You have to multiply k with 8k to get 8k square. So you get 8k square plus 8k. That's all. Now you subtract. When we subtract, we get 26 minus 8 is 18k plus 18. Then you multiply with, you have to get 18k.
18.
So multiply with 18, you get 18k plus 18. So remainder you get 0. So it's a perfect division. So you get k plus 1 to k square plus 8k plus 18 upon 3. Look at what you want. K square plus 8k plus 18 upon 3. So this is equal to your right hand side. So this is all rough work. So therefore P of k plus 1 is true whenever P of k is true, and P of 1 is true. Thus, by mathematical induction, P of n is true for all n belongs to natural numbers. Because P of 1 is true, so whenever P of k is true, P of k plus 1 is true. Because P of 1 is true, P of 2 will be true. And because P of 2 is true, P of 3 will be true. Because P of 3 is true, P of 4 will be true. So like that, for all n belongs to n, this will be true because it's an increasing stepwise. All right. Clear? Do you want time to copy this down?
Yes, sir.
Okay. When you're done, you let me know.
Sir, completed.
Okay. Chaitra, how about you?
Completed, sir.
Okay. Next, we'll do problem 3. This is on another reciprocal sequences. Look at this. Prove by mathematical induction. This statement. 1 upon 1 into 3 by 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 2n minus 1 into 2n plus 1 is equal to n into 2n plus 1. So the first step is to write this as the P1, Pn. So let the statement to be proved be Pn 1 by 1 into 3 plus 1 upon 3 into 5 plus 1 upon 5 into 7, 1 upon 2n minus 1 into 2n plus 1. This is equal to n by 2n plus 1. So nth term has already been given. Otherwise, this would have been difficult to write the n term. So n term is given. It is not very difficult. We can write it, but this is given. Now, if so now first step is to prove that this is true for n equal to 1. To check, how did I write previously? Check for P of 1 to be true. Correct. We'll write like that. Check for P of 1 to be true. So LHS of P of 1 by 1 into 3, the first term. So it is 1 by 3. RHS is n upon 2n plus 1. Substitute n equal to 1. 2 into 1 plus 1. So 1 upon 3. Therefore, P of 1 is true. All right. First term for n equal to 1, this is true. Now assume that P of k is true. Assume that P of k is true. That means P of k is 1 by 1 into 3 plus 1 by 3 into 5 plus 1 by 5 into 7, so on, plus 1 by 2k minus 1 into 2k plus 1. Instead of n, we write k is equal to k upon 2k plus 1. This is equal to k upon 2k plus 1. So this is true. Now, given that pk is true, check whether P of k plus 1 is also true. So what is P of k plus 1? 1 by 1 into 3 plus 1 by 3 into 5 plus 1 by 5 into 7 plus 1 by 2k minus 1 into 2k plus 1 plus 1 by, now instead of k, if we write k plus 1 here, the nth term, 2 of k plus 1 minus 1, that will become 2k plus 2 minus 1. So 2k plus 1. The second factor will be 2 of 2k plus 1 plus 1. You will get 2k plus 3. Okay. So this term will be 2k plus 1, 2k plus 3. This should be equal to, right hand side should be k plus 1 upon twice of k plus 1. 2k plus 1, you will get 2k plus 2 plus 1, 2k plus 3. So this has to be true. So this should be true given that this is true. So take the left hand side, write this down again. This is the left hand side. Now in the left hand side, you have pk is true. So this term is true. So you get k upon, this should be k upon 2k plus 1. So let's see. So write this as k upon 2k plus 1 plus 1 upon 2k plus 1 into 2k plus 3. All right. So now let us check. Now let us bring to the common denominator 2k plus 1 times 2k plus 3. So here, to get the common denominator, you have to multiply this 2k plus 1 by 2k plus 3 in the denominator and in the numerator. Plus 1. This is 2k square plus 3k plus 1. This will be equal to 2k plus 1 into 2k plus 3. Now this numerator we can factorize. 2 into 1, 2. 2 plus 1 is 3. So we can factorize this as 2k plus k plus 1. So 2k plus 1 times 2k plus 3. You get take 2k common. You get k plus 1 plus 1 common. You will get k plus 1. Correct? So you get, so this factor is 2k plus 1 times k plus 1 by 2k plus 1. 2k plus 3. This 2k plus 1, 2k plus 1 cancels. We get k plus 1 by 2k plus 3, which is same as the right hand side. Therefore, p of k plus 1 is true whenever P of k is true. Okay. Also P of 1 is true. Therefore, by the principle of mathematical induction, P of n is true for all n belonging to n. Clear?
Yes, sir.
It's a standard process for all problems. You just need to practice it. If you practice, you will be able to do it. One more. Just a second. You have divisibility problems also. Okay, we can show this. Chalo. They are equality problems. I have covered. Let's do inequality problems and then divisibility problems. This is question 9 from the exercise. Show that two n plus 7 is less than n plus 3 the whole square. So solution is the statement to be proved for all n belonging to n is P of n is 2n plus 7 is less than n plus 3 the whole square. Okay, let's attempt this. Now let us start. So check for P of 1 to be true. So what is P of 1? Left hand side is equal to 2n plus 7, which is 2 into 1 plus 7, which is 9. Right hand side is n plus 3 the whole square. It is 1 plus 3 the whole square, which is 4 square 16. Therefore, LHS is less than RHS. Therefore, P of 1 is true. Next, check. Assume that P of k is true. So this gives 2k plus 7 is less than k plus 3 the whole square. Now, given that pk is true, check for p of k plus 1 to be true. P of k plus 1 will be 2 times k plus 1 plus 7 less than k plus 1 plus 3. All right. So now we just need to manipulate this one. So let us check left hand side of the inequality is twice of k plus 1 plus 7, which is 2k plus 7 plus 1. Now this is less than 2k plus 7 is less than k plus 3 the whole square. 2k plus 7 is less than k plus 3 the, oh I'm sorry, I made a mistake. This is 2k plus 2 plus 7. So you get 2k plus 7 plus 2. 2k plus 7 plus 2 into 1. So now 2k plus 7 is less than k plus 3 the whole square plus 2. This is given. If it is given that pk is true, this will hold true. Now we have to show that this term is less than this right hand side. Right hand side will be RHS is k plus 1 plus 3 the whole square. You take this as A, this as B. This is no, you take you rewrite this as k plus 3 plus 1 the whole square, which is k plus 3 the whole square plus twice of k plus 3 plus 1. So this is k plus 3 the whole square plus 2k plus 6 plus 1, 7. Now this we can write as k plus 3 the whole square plus 2 plus 2k plus 5. Now you see here, left hand side is k plus 3 the whole square plus 2. Right hand side is k plus 3 whole square plus 2 plus 5 at least. That means right hand side, and k value is a positive integer. So this value will definitely be greater than 0. Okay, so therefore k plus 3 the whole square plus 2 is less than k plus 3 the whole square plus 2 plus 2k plus 5. Correct? So left hand side, this now, therefore 2 times of k plus 1 plus 7 is less than k plus 3 whole square plus 2, which is less than this term, k plus 1 plus 3 whole square, that is k plus 4 the whole square. Therefore, p of k plus 1 is also true whenever or if p of k is true. Got it? This is inequality. Proving the inequality was slightly different approach. So p of k is assumed to be true. Now we do p of k plus 1. So we get this. Now left hand side, we have to simplify this term such a way that we can use the statement p of k. Now p of k has 2k plus 7. So that's why I expanded this left hand side as 2k plus 2 plus 7. That will be 2k plus 7 plus 2. Now this 2k plus 7, because from the statement p of k, is less than k plus 3 the whole square. So this whole term will be less than k plus 3 the whole square plus 2. Okay, if you add plus 2 both sides, this will be this term is less than k plus 3 the whole square. So this plus 2 will be have to be less than this plus 2. Okay, from the statement that pk is true. Once this is true, now once this is found like this, so now I want to check whether this is less than k plus 4 the whole square. How to check? I will write, because I have k plus 3 term here, I will write this k plus 1 plus 3 as k plus 3 plus 1 the whole square, and I have expanded. So now I get this k plus 3 plus 2 plus 7, but I have to compare with k plus 3 the whole square plus 2. So I write this as k plus 3 whole square plus 2 plus 2k plus 5. So obviously this term is lesser than this whole term. That's what it is. Okay, because there is a positive quantity in addition to the left hand side. Now this is greater than 2k, twice of k plus 1 plus 7, and this is less than this one, which is k plus 4 the whole square. So this means that this statement is true. P of k plus 1 is true. So therefore, thus by mathematical induction, P of n is true for all n belongs to n. For all n belonging to n. Okay. You can, if you have doubt, you can go through this again, try it yourself and do it. In the beginning, this is little tricky. The concept of mathematical induction is not tricky, straightforward. When it comes to different types of problems, how to solve it, that is little tricky. So look at example 11. prove by mathematical induction. Four power n minus 3 power n minus 1 is divisible by 9. So this is now a divisibility problem. Previous problem was inequality problem. Now this is divisibility problem. So let us start. The statement to be proved for all n belonging to n is P of n is a statement that 4 power n minus 3n minus 1 is divisible by 9. Okay. So step 1, check for P of 1 to be true. So P of 1 is 4 power 1 minus 3 into 1 minus 1. That is 4 minus 3 minus 1, which is 0. And 0 is divisible by 9. Because 0 upon 9 will give you 0. Therefore, P of 1 is true. 0 upon any number is 0. So P of 1 is true, no problem. Assume that P of k is true. This means 4 power k minus 3k minus 1 is divisible by 9, which means this implies we can write 4 power k minus 3k minus 1 is equal to 9 times m, where m belongs to natural numbers. So some natural number m. All right, we can show that. So now, because it is divisible by 9, we can write as 9 into some factor. Now next, if P of k is true, check for P of k plus 1 to be true. That means P of k plus 1 states four times of k plus 1 minus 3 times of k plus 1 minus 1 is divisible by 9. So let us take this left hand side. So 4 power k plus 1 minus 3 times of k plus 1 minus 1 is 4 power k times 4 minus 3k minus 3 minus 1. Okay, see this, minus 3k minus 3 minus 1. So we get 4 times 4 power k minus 4 minus 3k. I will take 4 common. I'll get 4 power k minus 1 minus 3k. Now I can, to get this 4 power k minus 1 I have got, I have to get minus 3k inside this bracket. What I can do, 4 power 4k, suppose I multiply this with, I want to use p of k, right? I have to use this. If I have to multiply this with 4, I'll get 4 into 4k minus 4 minus 12k. So I have to get 12k. So minus 12k. To get minus 12k, what do we have to do? I have to write minus 12k plus 9k. I have to subtract and add 9. So minus 3k, I'm writing as minus 12k plus 9. So this will be 4 times 4 power k minus 3k minus 1 plus 9k. So because the second statement is true, this divisibility by 9 is there. So 4 power k minus 3k minus 1 can be written as 9 times some natural number. So this is 4 into 9 times m plus 9k. Now you take 9 common, you get 4m plus k. So 9 is a factor. 9 is a factor in the RHS. Therefore, which is divisible by 9. This is divisible by 9. Therefore, P of k plus 1 is also divisible by 9. So that statement is true. P of k plus 1 is true if P of k is true and P of 1 is true. Thus, by mathematical induction, P of n is true for all n belongings to natural numbers. Clear? This last two problems, little tricky. You will have to practice it again. See these notes. I'm just now sharing in the WhatsApp group. In another 5 minutes, I'll share this in the WhatsApp group. As I told you, open with Adobe Acrobat DC and change the page color. You will be able to see this. All right, I'll stop for today.